Okay, so your assignment number 4 has just been released. This one, feel no pressure. There's no associated, there's no programming test to cover that, but just to complete your learning about trees, just part 2. So you can just try more exercises on the tree. I still got office hour next week. Also, I'll try to host some special office hour during the exam period. You can definitely reach out to me if you got any question about the assignments or course material in general. And there will be one more makeup lecture for this week's programming test number 2. I will announce that sometime next week. I haven't decided yet exactly how we can fit that makeup lecture into the last bit of the course, but I'll let you know for sure next week, so you don't need to worry about it for now. And our exam is actually on April 20th. It doesn't really hurt for you to really get started about preparing for the exam. So in the last class, next Thursday, I will give you guys some idea, some preliminary information about the exam and how that's going to be organized or coordinated between all the 4 sections and what kind of information you really want to pay attention to for our sections. Okay, I'll give you the more information next Thursday. Just make sure you come. Okay. All right. Any question about the course? Okay, good. Let's do some recap. So last time, we actually finished the last bit about the quick sort and merge sort and then the quick sort. Okay, let's now do very quickly the recap. And for the merge sort, we actually look at the tracing over here, and we try to provide you 2 insights over here. Number 1, how many splits do you really have to do to really split from the original array down to individually just one singleton list, right? That's kind of automatically sorted for each one of them. It turns out you need log n. That's really the minimum heights for a full binary tree. And then for each level over here, the number of comparison you have to do in order to merge is going to correspond to the sizes of all the lists added up together, which will be just n. So you got log n level times n work, like a comparison in each level, that'll be n log n. So that's a very important visual summary about how the merge sort is going to work. It's always going to be n log n because it's guaranteed whenever you split the array into half, it's exactly half n over 2. And we look at the recurrence relation for merge sort. You will see that it is exactly 2 times t of n divided by 2, right? And the n over here is about the merge that you have to do for every level, every time you make a recursive call. All right, so you guys want to be very comfortable with given some piece of Java code and what will be the corresponding recurrence relation. So far we have done the example for binary search, merge sort, and also quick sort. And for quick sort, we actually did 2 variants. One is about the best case, the other one is about the worst case. So these 2 are also important to distinguish. I'll get there once we recap about quick sort. And then we actually did it from scratch about how you can unfold the recurrence relation for the merge sort, right? That's something you guys will have to make sure you know how to do during the exam. I might give you something very similar or maybe something you haven't seen before, but at a similar level of difficulty, right? Just make sure you got very familiar and also comfortable of doing unfolding yourself from the recurrence relation. All right, so that's about merge sort. And for the quick sort, we got some visual summary over here about how you can understand it at a high level. It's really about pivot selection. That's the most important step. You got to make sure the pivot you actually choose ideally should be very close to the median value so that when you try to partition around the pivot that's median, then the number of elements that's strictly less and the number of elements that's strictly larger than will be roughly equal. So you still got n divided by 2 and n divided by 2, for the 2 sizes. That's a very critical insight about getting quick sort into its best case. On the other hand, what we learned last time was in the worst case, if you somehow choose the pivot such that everything that's to the left or to the right of the pivot basically is the rest of the list. In that case, you just got linear number of partition that you got to do, right? So when you guys look at the recurrence relation for the worst case, there's some mistake I made last time. I want to correct it, and thanks to one of you actually corrected me after class. So recurrence relation here should be t of n. What I incorrectly put was t of n here. Of course, that's infinite recursion. You should always strictly reduce the problem size for the recursion. So this should be n minus 1. So why is that an n minus 1? Think about n minus 1 is we just got rid of the pivot value, which is not included in the recursive call. So let's say if we choose the pivot over here, and somehow the pivot is right here, and all the rest is the n minus 1. Right? It's kind of linear. So this will be the worst case where you got very unbalanced split or partition of the two halves. On the other hand, if you can choose the pivot value so that you got roughly equal sizes of the two partitions, in that way you'll get 2 times T of n divided by 2. That will be just like merge sort. Okay? So the best case for a quick sort will just be like a merge sort. But for the worst case for quick sort, it will just like a quadratic, like a selection sort and insertion sort. So these are the important facts you want to know about these two sorting algorithms, but also need to understand what's the rationale behind them. Okay, that's really what you're going to pay attention to. All right, so that's about from last Thursday. All right, do you guys have any question about these two sorting algorithms? Merge sort, quick sort? Okay, so when you actually review the sorting algorithm for the exam, you can see now we already got 4 of them. Right? So we're going to cover one more before the end of the course, which will be heap sort. But before that, we need to cover something called binary search tree, which we'll do from today. Okay? So if you have no further question, why don't we continue with the binary search, right? So it's a new lecture, so you can look at the lecture site. The slide is already there, binary search tree. So we are only going to cover about half of it, and then I will decide whether we're going to do the other half as a makeup lecture, so I can do something different next Tuesday and Thursday, or something else, but I'll confirm. So for today, you don't need to worry. We're going to cover the foundational stuff for binary search tree. So binary search tree, we should really understand, first of all, BST, right? That's usually a short form for binary search tree. It's basically binary tree, which we know pretty well from the previous lecture. Binary tree, and then you really want to recall what's kind of the bounds on the measure. Given n nodes, what will be the lower bound and upper bound on the heights, for example, right? Those kind of stuff. You want to make sure you kind of recall those information. And it's really about binary tree with the so-called search property. And that's the first thing we're going to dive into details about search property, right? Any binary tree that satisfies the search property, we can call them binary search tree. Okay, we'll talk about it in just one moment. And we're going to see how we can implement some generic binary search tree in Java. It's going to be a little bit simpler implementation than general tree, because now we don't really need a singly linked node to store the children. We don't need to. All we got to do is we need 2 references, left and the right, branches out 2 times. That's something we'll see also towards the end of today to see how I can build a binary search tree node in Java. And we're going to talk about either in the makeup lecture or next Tuesday about how you can do searching, how you can do insertion, how you can do deletion. Deletion will be the most complicated operation, where you got to discuss the operation in different cases. And that's something we have to discuss later. Okay. All right, let's now talk about recursive definition for binary search tree. The way to define a binary search tree is to say, given a binary tree, how can it satisfy the search property? And the search property, you want to remember, number 1, it is not a single property you will apply just once on the absolute root. Now, really, you have to make sure you apply the property recursively, right? That's something I want to emphasize right away. Okay? But let's see exactly how to define that. So we say a BST is a binary tree satisfying search property, which is the following. We're considering every internal nodes. We don't really consider external nodes, just internal, okay? Which means some nodes that has certain children. And because you got children, so that means you got left subtree and right subtree, right? The terminology we explained earlier. And now we have a new concept called entry. Okay? Each node in the binary search tree doesn't store a single value. They store something called an entry, which contains a pair, 2 things. Okay? One is called key, the other one is called value. So that's why in the slide you will see something called key value pair. All right? I'm going to explain that a little bit deeper. Okay? And if you look at the textual definition, this is the search property. Right? And I will also visualize that right now. Okay? Let's talk about it. So this is one example of binary search tree, which we'll try to verify the search property in just one moment. But this will be the general structure for binary search tree. Okay? Let's start with the root over here. And the root here, let's call it P for parents. Okay? P over here. And the node P stores 2 things as a pair. First of all, you can think about the whole thing over here is an entry, the whole thing, which contains the key and the value. Okay? The whole thing is called an entry. And inside the entry, we actually got 2 things. One is the key, the other one is the value. So we got the key of the parent node, okay? And it is very important to know the purpose of declaring the key. The key is only for searching purpose. It's not supposed to store any like a business data, just for searching, okay? It is for searching. And because you're using something for searching, it must be unique. There should be no duplicates. Otherwise, it got ambiguity when you're searching for a particular key. Right? So there should be no duplicates. Right? That's very important. And the other part of the entry is something called value. That one is more like a data value. Could be a string, could be an object, could be integer, whatever you like. And that one there is going to be value. Okay. So this one here will be the data value. And it's not really meant to be used as for searching purpose. So you may contain duplicates of the data value. That's absolutely fine. Like if you store an array, it may contain duplicate. The same idea. May contain duplicates. Right? Entry contains two things: key for searching and value just for business data. Right? So that's the concise way of understanding it for each node. However, for our illustration about searching, insertion, and deletion, we normally only focus more on how the search key is going to be used for manipulation. So the value you see over here, think about it, we're just omitting the actual data that's being stored. Right? We're just omitting it. You can easily just use, once you get a node object, you can say the node object dot maybe get data or get element, something like that. But we just don't show that in the visual diagram. So whatever value we show, for example, 44, 17, so these are all the key value. Okay, so key value here, just to clarify, key and value. All right, so each node stores an entry. What about the search property itself, right? It is saying the following. For every internal node, for example, the absolute root is an internal node. It has a left subtree. Also, it has a right subtree. Okay, let's now identify them, and then I'll state the property. So this guy here is the left subtree. Okay, and this one here is a right subtree, which may contain an arbitrary number of nodes in the subtree, right? Can be arbitrarily big. Okay, so this one here is the right subtree, and this one here is a left subtree. Okay, these two. And the search property says the following. If you take the key value over here from the root and compare with every node's key value in the left subtree, here's the property, the first half. Every node in the left subtree, their key value must be strictly less than the key value of the root. Every node. Okay, part number one. Part number two, every node in the right subtree over here, their key value must be strictly larger than the key value of the root. Let me write it down first, and then we'll see some example. Okay? And the most precise way to express this property here is by using the universal quantification, which you learned from 1019, right? Why don't we do it together, okay? So let's say for the left subtree, the search property tells us for every node, n is a member of the left subtree of P. And it is the case that the key of n strictly less than the key of P. Okay, it's a very precise definition about the search property, first half. And symmetrically, if you look at the right-hand side, the right subtree, it will just be larger than. Okay, let's now write these two properties down formally, and then we'll verify them on the example. Okay, and then the second one here is going to be, let me change the green. It's going to be, say, for every node, n is on the right subtree of the parents. It is the case that the key of that node in the right subtree must be strictly larger than the key of the parents. As you can see, so here it's larger than as opposed to smaller than, right? Symmetric. Notice that we didn't say less than or equal to, and also larger than or equal to. It's because we don't allow any duplicates, right, for the key. All right, let's now try to verify these two very quickly. For example, let's say this is the root right here, right? And as far as this root is concerned, the left subtree is right here. This is the left subtree, right? Now try to look at every node in the left subtree. We got 8, 17, 32, 28, 21, 29. All the key values in the left subtree are strictly smaller than 44, right? That's one thing. And then if you look at the right subtree right here, the right subtree is here. And look at all the nodes, their key value in the right subtree. 88, 65, 97, 54, 82, 93, 76, 80. They're all strictly larger than 44, right? So we just double check these two properties over here. However, what we just check is only for the root of this particular subtree over here. Remember I said in the very beginning, the search property is not meant to be checked for only one single root. It's meant to be checked recursively. And to really define something recursively on a tree, you have to talk about subtree. So the way to understand this would be, you want to make sure the search property holds on every subtree's root. I'll write it down, okay? So the search property here is meant to be checked recursively. Should hold recursively. Okay. On the root of every subtree. So the first keyword is about recursively, right? And also the root of every subtree, right? It's a really important point. How do we apply this? I'll give you some idea. So the search property we just checked is with respect to this particular root. So what about this particular subtree over here? To really check to see whether or not that subtree is also a binary search tree, what we do is this root over here, and then we got left subtree, we got right subtree, and then check those two properties again. Okay? With respect to this particular root, we got the left subtree over here, and also we got a right subtree right here, right? And now let's verify those two universal quantification. Every node in the left subtree, we got 8, which is strictly less than 17. And also every node in the right subtree, the key value 32, 28, 21, 29, strictly larger than 17, right? So all you got to do is you got to make sure you check this search property here for every subtree on its root. You got to do that. How many subtrees do we have, by the way, in this tree here? How do we calculate how many subtrees are there? If you guys remember. How many internal nodes, to be more precise, okay? So how many subtrees do we have, okay? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 internal nodes, okay? Of course, you can define this binary search property, like a search property recursively, okay? However, there's one way that's gonna allow you to check more efficiently. If I give you some diagram to look into, but I'll talk about it. It's another property, okay? And I want to talk about one special case. So guys, take a look at this particular tree here. This tree is what I would call a singleton binary search tree in the sense that it has only internal nodes over here. And somehow these two external nodes are what we call a guard nodes. That's something I'll mention that a little bit later, okay? So this is the smallest binary search tree you can have, like a base case. But how do we argue that this particular binary tree is also a binary search tree at the same time? Using these two quantification. Let me say that again, okay? I'm gonna talk about this one in detail. I want us to consider the smallest binary search tree possible, which will contain just one internal nodes and two external nodes. In that way, how do we see this particular smallest binary tree will satisfy the search property here and the search property here? So that's our challenge. Okay, let's now talk about that one there. Okay. Before that, let me just do one more clarification. You might be wondering, why do we have like a circle versus square All right, so that's something I want to clarify. Okay, so if you look at the slides, it actually said something there. Okay, so if you go to, yeah, exactly here. If you go to slide number 4, it tells you for our convention, so the internal nodes are going to be circle. And we're going to create something called sentinel, like a header and trailer in the doubly linked list, right? If you remember, the way we create a header and trailer for doubly linked list is to really improve the code structure, so we can easily write some algorithm by simplifying the code structure. That's something we'll see in the later lecture to see how exactly we can define the search, insertion, and deletion by using the guard nodes. It's going to be simpler code structure, right? We'll see that later. Okay. So as far as today is concerned, you can think about there are 2 kinds of nodes in the tree. What I'm going to color as green, so these are the internal nodes, which store some meaningful key value. Okay, so these are the internal nodes. On the other hand, for code structure simplification, we're going to say each internal node at the bottom level, they also got 2 external nodes accordingly, right? Over here, over here, over here, over here, over here. So we're going to see some Java definition for today. The way you create either internal node or external node, you're going to use different constructor, like an overloaded constructor, which we'll see. Okay. External nodes, for example, this guy over here, does not store any key or data value. They're simply just null. They're only like a placeholder for us to improve the code structure. On the other hand, for each internal node, like in green, they do store some meaningful key and data value. Okay. All right, having said this, let's now consider the smallest binary search tree like this. Okay, let's talk about it. Okay. All right, so let me now just draw something very quickly. Well, we talk about the smallest one, like a singleton, right? So let's say we got the internal nodes over here. Let's say it stores the key value x. And then let's say we got some node reference over here called P, parents. So this is an internal nodes. And that one there simply got 2 children, let's say, 1 and 2. So external, external. So we're saying that these 2 nodes are just external nodes. You can also think of the tree rooted at the left child, which is external nodes, is going to be a left subtree. The tree rooted at the right child here is actually here, right subtree. Okay, that's another way to look at that. Over here, this will be the left subtree. And over here, it will be the right subtree. All right. Having said this, let's now take a look at, let me say one more thing here. When we talk about the external nodes, so these are like the header and trailer that we saw earlier in the doubly linked node. They're like the header and trailer in doubly linked node for the same purpose. It's really just for code structure. They don't really help improve the performance for the algorithm. Just make the algorithm implementation a little bit simpler, more maintainable. And does not improve performance. Does not improve performance. All right, just make a note here. All right, so now I'm going to show to you guys very quickly how can we apply the search property on the left subtree and the right subtree to show that for this particular smallest binary search tree, why it will satisfy the search property, right? I'm just gonna rewrite the property here. In order to satisfy the search property, I'm going to say for every node that's in the left subtree of P. So I'm referring to the left subtree over here. Okay. Then it is the case the key of the node is strictly less than the key of the parents. Right? You can think about everything here is less than, everything here is greater than. So that's the first half, and the second half will be about right subtree. So for every n member of the right subtree of P, it is the case, the key of that particular node should be larger than the key of the parents. Right? So that's something we just learned in the last page. Now we want to see why these two parts of the search property will nicely satisfy the left subtree and the right subtree trivially in logic. All right? Can anyone somehow see why this will be the case before I tell you the logical property you can use?
Is it because it would just reduce to the case where there's none? So then trivially, because there is no key that satisfies all?
That's exactly right, Ben. Exactly right. So to be more logically clear, we are basically talking about the following property, which I'll write it down here. So back in 1090 or 1019, you might say for every x, if I got false over here, implies P of x. All right? If somehow the antecedent here is false, does it really matter what this is? Not really. The implication will just be true. All right? So that's something you guys can feel free to review, just this fact over here. This is something called zero of implication. Zero of implication. And this one here is just going to give you true, meaning that whenever you want to prove about the implication, if you can show that the antecedent is already false, it doesn't really matter what the consequence is. The overall implication will just be true. How do we apply this property here to here? As Ben correctly pointed out, we can argue that the left subtree over here, the left subtree of P, and also the right subtree of P over here. If you think about these two subtrees, they only contain the external nodes. But remember, external nodes doesn't store any meaningful key value. So it'll be as if there's nothing here, like empty. So you can easily replace this one here just by empty set, and this one here just by empty set. Okay? And what does that mean? That means n is a member of empty set is always false. N is a member of empty set is always false. So you do fall into this particular property over here. All right? So this part over here is going to give you false. And this part over here is also going to give you false. And by this property here we just spoke about, you will know that this implication and this implication will just be true. And then you got true and true. So the search property will be satisfied by this minimum binary search tree over here. All right? It's a little bit more logical argument over here, but I think it's nice to know. So this is just to show you that in the base case, where you got the smallest binary search tree possible, how is it actually argued as a binary search tree, right? That's the main point. Yeah, think about it. Okay. All right, any questions so far? We good? All right. All right, if we're good, let's now talk about something called sorting property, okay, for binary search tree. All right, so let's now talk about a sorting property, okay, which will go nicely with the search property that we just spoke about, right? So these are the two important properties in order to understand binary search tree. If you look at the slides, we are done with slide number 4 and also slide number 5. That's what we want to do. So the sorting property, let's read the facts first, and then we'll see how exactly it can be understood. This one here does require quite a bit of a visualization, which I'll do. This is to say, if you know that you have a binary search tree, which satisfies the search property that we spoke about earlier, and then you try to run an in-order traversal on the binary search tree, what you're going to get is maybe an array or maybe array list or singly linked list of nodes. is guarantee the keys in that particular chain of nodes is going to be sorted in the ascending order. By the way, ascending but not non-descending, because we don't allow any duplicates, right? Notice the work selection over here, right? We do not allow any duplicates of the keys. So that's why when you say non-descending over here, it's not right, because non-descending does allow some duplicates, as we said earlier. You can review the earlier lecture. All right, let's now try to see the correspondence, okay? Let's now try to look at that. By the way, so that what I just said here is the facts. That's something you have to know, but we're going to see the visualization to justify. Okay. So let me first of all write it down here. Okay, so we're saying that given a binary tree, that is a binary search tree. Okay. Number one, we know that the search property must hold recursively, right? That's something we just know. Number one, the search property is satisfied. And recursively, by the way, it must be satisfied for the root of every subtree. And number two, if we try to do some in-order traversal, let's imagine what's going to happen. In-order traversal. Or sometimes I just say IOT, right? In-order traversal. Okay. Let's see what's going to happen. Let's remind ourselves the pattern for in-order traversal. You can go back to maybe the general tree lecture where there's one single slide that we summarizes about the pattern for pre-order, in-order, and post-order. It's all a matter of when you add the order of recursively visiting the child nodes, really, right? For in-order, you will go with this manner. So let's say we got our parent node, P, okay? Let's say this is the P. And then we have some left child over there. And then we have some right child over here. And of course, this will be the left subtree that's rooted at the left child. Right, you can see we got left subtree over here. And this is the right subtree rooted at the right child of P. Okay, right subtree. And the way we do in-order traversal, let's now remind ourselves. In-order traversal of P. We should really try to do a recursive call on the left subtree, right? We're going to do in-order traversal on the left child. It's as if we're trying to do in-order traversal on the left subtree. And we start with the root of that particular subtree, right? And then after that, we're going to visit the P, the parents, which is not recursive, just a single node. And then after that, we're going to make another second recursive call on the subtree rooted at RC, the second right child. Right, you can see here, this will be the right subtree, and this will be the left subtree. Right, so that's in-order traversal. Okay. And we're going to put everything together, just one moment. I'll write it down as well here. So we do basically in-order traversal on the left subtree. Oh, you know what? Let me write it there. So I do have enough space. This can also make my point a little bit even more explicit. Okay, I'll put it here. It's going to be the in-order traversal on the left subtree. And also, it's going to be the in-order followed by the parents. And followed by the in-order traversal of the right subtree. Okay? Now, let's see this. What we know is, what do we know about from the search property for the left subtree?
All of its keys must be less than
Okay, very good. So that means all the key values in the left subtree must be strictly less. Very good. And symmetrically, all the key value on the right subtree must be strictly larger than. And since we're going to do in order traversal recursively, we're going to see that by doing also, even inside this one here, when you look at, for example, this one here may also got left and right. You're also going to do in order traversal as well. So it turns out you're going to get sorted sequence from there. But we're going to see exactly. Okay, I will show the correspondence. I want to ask you one more thing before I write, after I write something down. So this one here is going to be a sorted sequence of all keys in the left subtree. And this one here is going to return to you a sorted sequence of all the nodes, all the keys in right subtree. So this will be what's really from the first recursive call. That's from the second recursive call. This is a sorted sequence. This is another sorted sequence. And when we put together with P, we get a larger sorted sequence. Does this sound kind of familiar? That we spoke about last Thursday. Do you guys remember? The other one. Quick sort. How come? It's like a median or the pivot, right? Okay. So guys, this is something I would like you to connect when you study, okay? Somehow the P here, the pair is more like a pivot that we have chosen. And the in order traversal on the left subtree is going to give you some sorted left. And the in order traversal on the right subtree is going to give you sorted right. And you can simply concatenate them together without having to merge them. So this process here is similar to the concatenation process for quick sort, right? That's something you want to think a little bit more about. Okay, I'm pointing out to you. Okay, this one is a little bit similar to the concatenation in quick sort. Not really merge, okay? Think about it, okay? All right, let's now do some very quick verification, okay? So let's say there's a binary search tree over here, and then can you guys spend about 30 seconds, given this tree over here, what is the in order traversal? For those of you who got a tablet or got paper or computer, whatever, what's the in order traversal? Write it down. Yeah, 30 seconds. You can even think about it in your mind. That's okay, right? And ask you the following question to yourself. If you try to do the in order traversal, are you getting an ascending sequence? All right. This one brings up my earlier point. There are two ways for you to say, given some arbitrary binary tree, you want to know whether or not the binary tree is also a binary search tree at the same time. There are two ways to check it. Number one, you can try to check the search property recursively by considering every internal nodes. That's not very efficient. I mean, by hands. Another way to do it is, why don't you just do an in order traversal of the whole binary tree? If the resulting sequence from the in order traversal is a sorted ascending order, you know it's a binary search tree. That's the second way. All right. Let's now do one more thing, and then we'll take a short break, right? This one will hopefully wouldn't take long. But this is a very important comparison for you to see. Okay, let me just do that now. First of all, let me write down the in order traversal. In order traversal, okay? So we got 8, 17, 21, 28, 29, 32, 44. If I miss anything, please let me know, okay? So 54, 65, and then 76, 80, 82, 88, 93, 97. Okay, we're good, right? Okay. That's ascending order. So I just verified that it's a binary search tree. Okay, so that's a more efficient way. In the exam, if I only ask you whether it's a binary search tree or not, you can use this way. On the other hand, if I want you to demonstrate to me about search property, you got to do it another way, right? It depends. Now, I want to show you some very important visualization here. Think about the structure right here is the more nonlinear and hierarchical structure that we spoke about, right? This one here is nonlinear, it's a tree, hierarchical structure. On the other hand, the in-order traversal gives me a linearized version of the tree. Linearized version of the tree. Of course, there might be different linearized version you can create. You can do a pre-order traversal, you can do a post-order traversal, but we're doing in order right now. Right? So this is just linearized version. Okay? So we're talking about nonlinear versus linear, right? So that's a very critical difference that we spoke about earlier. Nonlinear versus linear. Okay, good. Let's now see the correspondence. Okay, let's start with the minimum, right? We spoke about the minimum binary search tree should be the one like this. Just one internal node with two external child nodes. Okay, so let's now identify them. So I got one here. I got 21 over here. I got 29 over here. And then I got 54 here. Okay, also I got 80 over here. Also I got 93 over here. So these are the minimum binary search trees I can find. All right. And let's see where we can find them in the sorted sequence. Okay, so for example, you can find 8 here. And you can find 21 over here. You can find 29 over here. You can find 54 right here. And then you can find 80 over here. And then finally, we got 93. Okay, I'm kind of showing to you how you can build a binary search tree bottom up and see the correspondence in the linear sequence. It's a very important visualization you want to see the correspondence. Okay, and let's now try to make the construction bottom up. For example, how about this one? That's strictly bigger. All right, let's start with this. This is the minimum binary search tree. Correspondingly, this is the minimum sorted sequence, just one element. This is sorted, this is also sorted, this is also sorted. The concatenation that we spoke about earlier is like this. I got 20A here, which correspond to the root. I can simply join this one with the 2 subtree, meaning that I'm going to concatenating the corresponding sequences together, right? So what I have is this one here. If I want to figure out the sorted sequence for this particular binary search tree, the way to do it is do the in-order traversal on the left subtree, which is this sorted sequence. Do the in-order traversal on the right subtree, which is this sequence over here. And then join them with the root, which should always come in the middle. That's the order we have for in-order, right? So the blue one here is a sorted sequence for just this subtree. It's a very important correspondence you want to see. All right, and let's just make it complete. Right, let's identify other subtree as well. Let's do another one here. How about this one here? This one is a little bit more interesting. Right, you can see for 76 over here, it's basically the root right here. So 80 corresponds to over here. But 76 doesn't have any left subtree. It's empty. So nothing else to really concatenate, right? So this one here simply corresponds to just this one here. All right, just like that. So if you try to do in-order traversal for this binary search tree over here, it's just going to give you the sorted sequence of size 2, where the left-hand side for the root is just empty. Nothing to concatenate with, basically. All right. And then let's do one more. What about this one here? This one here is kind of symmetric. We don't have the right subtree, right? So for 97, doesn't have a right subtree, but you got 93. So that's the one. Okay. So that is the one we can identify right here. Okay? Any questions so far? Right? You can see the correspondence, right? And let me remind you again before I continue to complete it. You really want to think about how this kind of process here really compared to the concatenation in quicksort. In quicksort. Okay, very important. All right, what's the next subtree we can look at? Let's say we look at, let's say this one here. Okay, what about this one here? So this one here, basically we try to join the 82, right? So 82 join with this particular subtree of 76 and 80. 82 doesn't have any right subtree, right? So what we got is like this. Okay, right here. And then why don't we try this one here? What about 65? For 65, is basically going to join two subtree. So 65 is right here, which is going to join 54 right here, and also this purple subtree, which corresponds to this purple sequence over here, right? All right, so that one there is going to be this. Okay, you get the idea, okay? And then let's say we got another one here. What about this subtree here? So this one we got 32. Basically this one here. And then we can do another one that's going to join 17, right? This one here. So this one here, let me just illustrate again. We got 17 right here, which is going to join 8. And also this pink subtree corresponds to this pink sequence right here. Right? So that one there is going to be like that. And you can see the orange sequence over here, the entire thing corresponds to the in order sequence for the whole left subtree, for the absolute root. Okay. And one final one. What about 88? All right, so that one there, let me make it green. This whole thing over here for the green is going to join the pink right here, and also the blue right here. And the root in the middle is 88. All right. So that's the final bit. So this one here is going to give us the right subtree for the absolute root. And of course, if you want to see the in order traversal for the whole thing, you're just going to concatenate this one here and also this one here and put the root in the middle. Right? You can see this whole process over here. Very systematic, right? Kind of build it from scratch to show to you. So the main takeaway from this page over here is you want to see, based on some binary search tree, how you can build that particular sorted sequence and see the correspondence. Right? That's really the main thing I want to show to you. All right, any question? Very good. All right. Why don't we take a very short break, and then we'll do some exercises and one more property, and then we can do some Java code. Okay. Okay, so before the break, we already finished covering the sorting property, right? So these are, excuse me, we don't really actually do any mathematical proof about the in-order traversal is going to give you some sorted sequence. But I think some justification, if you can see the 2 bullet points, that should be enough, right? We don't need to worry about too mathematical proof for this. And, okay, that'll be Java code, is for later. But I want to do several things to really conclude about the, give you guys more insight about the search property and the sorting property. Let's first of all do some exercise over here. All right, so this is the tree that we just got used to from the earlier exercises, and that's the in-order traversal, which we know is sorted sequence, right? Let's say this. I'm going to now modify one of the key value in the node. What you guys gonna tell me instead is whether or not after the change, is the tree still a binary search tree? All right. So let's say I'm going to change the value over here for 76 to 69. Is this still a binary search tree? Oh yeah? Okay, there are two ways for you to check this, right? We want to find the minimum impact spot over here. You can see what we are impacting is just this particular subtree. If you look at that, every node in the left subtree, which is 69, is still less than 82. Every node in here, oh, let me say it again, sorry. Every node in the left subtree, which is 69 and 80, is still strictly less than 82. And there's nothing in the right subtree. So, satisfy the search property. Another way to look at, you look at the resulting sorted sequence, which I want to highlight. Okay? So you guys can see that this particular subtree is being impacted right here. Let's identify where this subtree is, which we did thorough exercise before the break, right? So it's going to be right here. Right here. Right? Agree? Right? So that's the subtree in the pre-order. So we got basically 76, 80, and also 82. And we are basically just modifying this 76 into 69. As you can see, somehow the 69 is still in between 65 and 80, so it remains sorted. So that's why it's still a binary search tree. Okay? Let me write this down first, and then I'm going to give you a little bit more insight. This is okay because the 65 still strictly less than the 69 and still strictly less than the 80. As far as the linear sequence is concerned, it's still sorted. Okay? And I want you guys to somehow be a little bit more insightful here. Okay? So we say that 65 is the predecessor. Of the 69. And we say that the 80 over here is the successor. It's very easy to see in the linear sequence, of course. Let's see where they are in the tree. All right? Now let's look at 65 right here. This is the predecessor of the 69 in the in-order traversal. All right? And then the 80 over here is the successor. Successor of the 69 node in the in-order traversal. Right? You can see somehow we are considering for this particular node, its predecessor is actually here, but its successor is actually right here. Why? Right? So the way to think about it is, when you try to do in-order traversal, I do 54 followed by 65, and then I do 69. And then I do 80. So that's why predecessor and successor. Right? So you really want to be very familiar with the in-order traversal, right? So the way to see that in the tree is not as obvious, but you got to really see how the in-order traversal is done. Okay, that's my point. Okay, think about this one here, but let's do one more. Okay, the same tree over here, but I'm going to modify in a slightly different way. Okay, so why don't we try to replace, let's say, the 65 over here by 83. Is the resulting tree still a binary search tree? Is it? Not really, right? Well, I can tell you that intuitively I can see something wrong already. This is 83 the root. 82 is actually less than that. No way. Right? It already violates search property. Right? But let's see exactly how. So this one here is impacting this particular subtree. Right? So let's now identify the corresponding sequence. So 83 is right here. Oh, 65 used to be here. And then we got 54 all the way to 82. We're impacting this particular sequence right here. Right? And we were modifying 65 into 83. Apparently, 54 less than 83 is true, but 83 less than 76 is not the case. False. So we are violating the search property, or just the resulting sequence there is no longer sorted. Right? That's one another way to look at that. All right, one more thing for us to identify. You can see that this is a predecessor. Okay, let me just be sure. Okay, predecessor. And this one here is the successor. Relative to the node we are changing, right? Predecessor and successor in the in-order sequence. Let's see where they are in the tree. So for this one here, the predecessor is 54, right? It's the one before that when we do the in-order traversal. So this one here is the predecessor. Predecessor of in-order traversal. And what about the successor? Successor is 76, is right here. And that one there is the successor of the in-order traversal. All right. So these two examples actually show you something very important. To really identify the predecessor and successor in the in-order traversal, we'll need that kind of insight when we do deletion. Whenever you want to delete some node from the binary search tree, you want to make sure the deletion does not give you a new tree that's not going to satisfy search property. The way to ensure that, you need this kind of insight. So I would say before next Tuesday, try to review these two examples more carefully, right? Just get yourself convinced. That'll prepare you very well for next week. Okay. All right, any question about these two exercises? Okay, one more summary, and then we can get to the Java code. Okay, this one here is also going to be lots of fun. Okay, to really see in the global sense about how the binary search tree is going to be structured. Okay, so let's say we got binary search tree. Let's say we got the root. Again, let's call it P for parents. P over here. So we got a left child, and we got a right child right here. And the right child here. So the left child and the right child. And of course, the subtree rooted at the left child will be left subtree. So let's say this one here is the left subtree. Left subtree. And the subtree rooted at the right child is the right subtree, right? Oh, sorry. I can draw better. Good. Right subtree, right here. Okay. So far we got 1, 2, and 3 nodes. Let me put 4 more nodes. Let's say we got 1 node over here, and 1. We got another node here, and 2. And we got another node here, and 3. We got another node here, and 4. For example, how do we get from left child into the M1? You can think about it, simply follow the left child link all the way to the last node, that's internal. And how do we find N2? You follow the right child link all the way to the bottom, right? And etc., right? So now we got N1, N2, N3, N4, LC, RC, and P. All right. Can you just tell me, as far as these 7 nodes is concerned, what's going to be the order of them in the in-order traversal? Anybody? 7 nodes. Of course, there might be something in between. Let's not worry about them just yet. Which one should go first? N1? And then? Left child. Okay, and then? N2, and then? P. And then N3, and then right child, and then N4. Okay, guys, very good. Okay, let's now make it even more general. Okay, I'll make it complete, and then I'll make some remark. So we start with N1, and we might have some in-order traversal for the rest. Somehow we go backward. You can think about, we're going to go with this particular tree, right? We're going to go for N1 first, and then the rest, which will be here. Okay. followed by the left child. Let me make this one a little bit shorter so I got enough space. We got something over here. And then we got the left child, followed by something, and then we get to N2. And then after N2, we don't have anything in between. We go to P directly. And then we go to N3. And then we go for something. And then we go to the right child. And then we go to, over here, something. And then we go to N4. All right, so that's the in order traversal, right? So we got 1, 2, 3, 4, 5, 6, 7, all the 7 nodes, right? Okay, let's see what is so special about these 7 nodes. To start with, this N1 over here is the absolute minimum in the binary search tree. How do I tell? For example, follow the left link. 8 is the absolute minimum. That's the first one in the sequence. Symmetrically, 97, the rightmost child, is the maximum, right? So this one is the absolute minimum. And this one here is the absolute maximum. Okay. And now what we want to see is what is really N2? From a linear sequence, it's not difficult to see this, but it's going to be defined in a way that sounds a little bit unintuitive, maybe to some of you. We know that everything here is strictly less than P. However, out of those that's less than P, N2 is the maximum. Agree? Okay. So this is the largest key. That is strictly less than the key of P. It's a very important property for you to see, right? So we are saying that N2 over here is the largest one for those that are strictly less than P. As far as this subtree is concerned, where every node is strictly less than P, for this subtree here, N2 is the maximum, right? That's the way to see that. What about N3? N3, because we know that everything in this right sequence here must be larger than that. N3 is the minimum of them, right? So this one here is really the smallest key that is strictly larger than the key of P. Okay. Also review this one here before next week's class. This one is also going to help you to understand the deletion when we get there. Okay. All right, this page here is very important to really see the like a high-level structure for binary search tree. And the details in the middle over here is not relevant for now. Okay, we're going to look at that maybe a little bit later, more closely. All right, any question? We're good? Okay, let me just... All right, so let's now do a little bit of Java code. So you'll see that on slide number 6, we actually got the definition for something called BT node. A little bit like a tree node class that you guys did for assignment number 3 in the practice test. Okay, let's now study that a little bit. It's actually not difficult, so I'm going to just highlight some important details for you. Number 1, you can see the class is generic, right? You can see E here, right? And then we got something called a key, and we got something called a value. And of course, these two pieces of information combined is called entry. So these two tell you is entry. What you could have done in Java, of course, you can define another class called entry and just make the entry object if you want to. So it's just the implementation decision. And then we got the link called parents. And also we got another 2 links called the left and right. So we don't really have the children being singly linked node like what you did for the assignment. Okay? And then we got 2 constructor over here. So this constructor over here takes no parameter. So this is the constructor for creating external nodes. In which case the key and the value will just be null value, just default, right? Storing nothing meaningful. On the other hand, we got another one here. That one there is going to pass the key and the value as parameter. So this is actually for you to actually create internal nodes, which we'll see some example very soon. All right. And you actually got some query, the Boolean accessor over here to determine whether or not the node is external or internal. You can look at the definition, right? It's very straightforward. You can take a look. And also we got accessor and mutator for key, also for value, and also for parents, and also for left, and also for right. Very conceivable definition, right? Very standard, right? For those ones, I don't need to waste your time in the class. You can take a look and see how you can play with them. Let's visualize very quickly about how a binary search node would look like. So what we have is we got parent, we got a node here, first of all. So let's say the node is called N, right? We got some attributes called parents, which might point to some other nodes. So I want to think about this is like a unique predecessor. However, having a unique predecessor doesn't really make binary search tree a linear structure because the successor is not unique, as we'll see. All right, we'll see that. And then we got key and the value. So in the middle compartment, you can think about you got some value called key. You also got some got another attribute called value, right? Key could be, for example, some integer. For example, search key maybe 23. And the value could be maybe some string value. Let's say Alan. Okay, key and value, the entry. And then we got left and right. It branches out, which will make it non-linear. So we got the left and also the right, which will point to other tree nodes, binary search tree node. So the way to understand this is this will make it non-linear. So these two over here will give you non-unique successors. And this again tells us tree is non-linear. Just a nice point to kind of repetition, right? That's something we said earlier, but you can now see it from a different context. And what you guys should really do when you study for the exam is to really see how the visualization for doubly linked node, where you got unique predecessor, previous, also you got unique successor, which is the next reference, right? Just linear structure. Okay. Right? And then we can take a quick look on how we can implement the in-order traversal. Okay, so in-order traversal here is a recursive helper method. Sorry, a recursive method. In-order traversal over here, the recursive call is called twice. In-order traversal here, and also in-order traversal over here. You can see we try to call over here. Let's see here. Also, the return value is an array list, right? That's something we did. We did something very similar before. And the input is actually some root. And you can see when we try to call the recursive, make the recursive call, root that get left and root that get right. And then we also try to get a root in the middle. That's exactly the pattern for in-order traversal, right? Let me visualize very quickly for you, and then we can move on to see some test case. So here we got a root that's given right here. And then you actually follow the get left. And also you follow the get right. And that one there is going to be recursively handled by the in-order traversal, right? There's a left subtree. And this one here is going to be handled by also in-order traversal on the right subtree. Oh, sorry. Right here. Okay. Right subtree. Right, take a look at here. It's very easy to see exactly how in-order traversal works. Okay. Right, a final bit I want to talk briefly is to see how we can construct a binary search tree and see how the in-order traversal will work, right? So let's say the binary search tree we want to construct is like this. Let's say we got each node is going to be an entry. Let me now put both the key and value here so you can see that. Let me put a pair, okay? We got a key value be integer 28 and also Alan. So I'm saying this is the key, this is the value. And it branches out twice, left and right. Let's say I got another node over here. I got another node over here. And let's say that's it. So these are the three internal nodes. I got 21 over here and Mark. Also, I got 35 over here and then Tom, Alan, Mark, and Tom. And let's do a very quick check. If you do the in-order traversal for that, 21, 28, 35. Indeed, sorted. Binary search tree. And we are also going to construct the external nodes, which I'm going to visualize as this, like a square. But you'll see exactly how those will also correspond to some objects. We'll see that in just one moment. So this is the the conceptual tree that we want to build in Java. Right? That's exactly how we can do that. Okay? So we start with creating the various nodes. So this is the first phase we're going to do. So the one I'm going to highlight in blue, 1, 2, 3. These are the three internal nodes. And also we got 1, 2, 3, 4. So these are the four external nodes, right? Let's see exactly how. So I'm going to just create these three nodes. So one here, and one here, and one here. Okay, these are the three. Okay. So I got N28. Also, I got N21, which is here, and N35. And 28, 21, 35. So 28, 21, and 35. Alan, Mark, and Tom. Okay. The value over here is Alan. And the value here is Mark. And the value over here is Tom. Right? That's for the internal nodes. And for left and right parents, we're going to set up in the second phase. What about the internal nodes? The internal nodes is going to be using the constructor without any arguments right here. 1, 2, 3, and 4. Right? Let's now duplicate this object here. That would be a little bit too complicated. What we do is we're going to create 4 objects here. 1, 2, 3, and 4. Each one of them is an object. So external node 1, 2, 3, and 4. External node 1, external node 2, external node 3, and also external node 4. All right, so these are all the objects we created in the first phase. Now in the second phase, let me show you just one example. It's very conceivable. N28 is right here. Set its left to be wherever N21 is pointing to. So left should be pointing to here. Symmetrically, N21, which is this object here, should set its parent to be N28 symmetrically. So that's what we're doing, right? So think about what we're doing here is by setting the left to be here and the parent to be here. The next line is going to set right child to be here and also the parent to be here. Right? And similarly, you can look at the remaining line, right, and trace them. So left here, parent here, right here, parent here, left here, parent here, right here, and parent here. Right? So these are all the pointers we're going to set up. Right? The final thing to mention, okay, and after we have set up this binary search tree structure, which is pretty much like a tree structure, right? Just a little bit easier. You got left and right and also parents. So what you want to look at is we got some in-order list. And the way to really construct this in-order list, which is an array list, is by calling in-order traversal from N28. Right? So that's the absolute root of the tree. Okay? And then you can double check to see the resulting sequence is 21, 28, and 35. So this is the sorted sequence that we have. Right? You can double check the test case and make sure you understand that. So this will be the sorted. Give me 30 seconds and I'm done. Okay. This will be the sorted in order sequence. All right. So what we have done here is about going over the basic about constructing a binary search tree based on a binary search tree node. And next Tuesday, most likely we'll try to continue with this and see how we can do searching, insertion, deletion. Thank you so much. I'll see you next week.